Okay, we're going to be covering section 5.5. This is part 1 of that. We're going to be talking about solving exponential equations and logarithmic equations. If you recall, those are inverse operations, so we will be using one to solve the other. Okay, we've got a couple of equations here. When we have a variable up in the exponent, those are called exponential equations. And we're going to start with a couple of different properties, one of which is called the base exponent property. So the same constraints happen when we have our usual exponential functions. Our a, which is our base, has to be greater than 0, so we don't have any complex solutions, and our a cannot equal 1. So when we have an a raised to the x, and it's the same value as a raised to the y, we can say that x equals y and vice versa. Alright, so let's go ahead and take a look at one of those. So here I have a base 2, and that's raised to a 3x minus 7. And then I have a 32, and on the surface of it, it doesn't appear immediately that this is a base 2, but if you stop and think about it, it is actually. So we've got our 2 times 2 is going to give us a 4, times 2 is going to give us 8, times 2 is going to give us 16, and times 2 is going to give us a 32. So I have the same as 2 to the 5th power. I'm going to go ahead and run through that. So we're going to solve this. All right, we've gotten to this point. We've said our 2 is the base. 3x minus 7 is going to be equal to our base of 2 to the 5th power. So we're going to take away the bases of 2 since they are the same. We can just kind of look only at the exponent part. So we're going to start with 3x minus 7 equals 5. And we're just going to do the algebraic steps in order to isolate that x. So we add that 7 to both sides. I'm going to divide both sides by 3. So we get x equals 4. We want to double check that that's true. All right, so we're going to go ahead and check. Plug it in, see. And we do get 32 equals 32, so we're good. All right, so property of logarithmic equality, this is also, it's very similar to what we just did, where we say that for any value of m, any value of n, and any value of a that are greater than 0, and a, again, cannot equal 1, if we have a log base a, m, and it's equal to log base a, n, then our m and our n are equal. So here I'm going to take my 3 to the x, and I'm going to figure out where that falls in 20. Well, first I want to double check that it doesn't give me a perfect one, and then we could just solve it real quick. If you stop and think about it, I know that 3 squared is going to give me 9, and then 3 cubed is going to get me 27. So I know that it's going to fall somewhere between a 2 and a 3, but there's not a nice exact number that's going to help us out here. So we're going to take our log base 3 raised to the x, and that's going to equal log 20, or I should say log base 10, 3 raised to the x equals log base 10, 20. We're going to bring that exponent of x down in front. All right. So now when I isolate this, I have the log base 20, or log base 10, 20, over log base 10, 3. And I want to point out that this log base 20 over log base 3 is not the same as this. It's not log 20 over 3. It is not. This is a change of base formula, if you stop and think about it. I realize that's not what our original intent is, but we can't just do this step. It doesn't work. So we actually have to take and find the values of log base 10, 20 and log base 10, 3, and then do the division. All right, that's going to give us a very different value than if we were to try and do just plain old log 20 over 3. I want to point out that this is our exact answer. If you are asked for the exact answer, this is what you're going to give. It's going to be the log base 10, 20 over log base 10, 3. That is our exact answer. Now, because it doesn't fall into a 2 or a 3, it isn't the exact values of 2 or 3, we know that this has to be irrational. All right? It's not going to be nice and neat for us. So we're going to have this really odd, 2.7268, right? That's going to kind of mess with our heads a little bit. It's approximate. It is not going to be exact. We call it close enough for the moment with 4 decimal places. When you're doing your assignments or homework or quizzes or tests, you're going to want to read your question carefully. So you will find out whether you need to do the exact value or whether an approximation and what decimal points you need to take it out to. All right, and then we're going to double check that we have in fact solved our problem. And so that's going to, when we do that, we're going to get close to 20. It won't be exact, remember that. And that's okay. All right, one more quick one before I end this video. All right, we have a 100 times e raised to the 0.08t equals 2500. Well, first thing I'm going to do is I'm going to get rid of these hundreds, right? So there's a step that they actually kind of jump over. So we're dividing both sides by that 100. So we have e to the 0.08t equals 25. All right. That's a nothing. All right, so then that's how this shows up next. We're going to use our ln so that we can deal with our e, right? And then we're going to take our exponent and bring it down. And the thing that, there's a step again here that they don't really tell us. After you bring this guy down in front, well, ln e is the same as log base e, which is the same as a 1. So that's how this becomes strictly 0.08t. Again, I'm going to go ahead and just divide both of those. And that's going to give me my t value, which is what we want. This again is my exact solution. This is the exact solution. All right. So if it asks for the exact, you're going to leave it just like this. If they ask you to approximate it, and they tell you how many decimal places, then you would do something like this. You would find out it's close to 40, and then you could double check. 40.2, right? All right. I'm actually going to pause the video at this point, and we will come back and start with this problem.